Thank you, Chairman, for the introduction, and good afternoon, everybody. This research is a part of my PhD research, which is done in the Laboratory of Waves and Currents in University of Rio de Janeiro, based on, about current energy extraction. Traditionally, current energy, marine current energy, is extracted using rotation-based turbines, whether horizontal-based turbines or vertical axis-based turbines. But to use of these rotation-based turbines has some disadvantages. For example, they need high Reynolds number currents so that they can have reasonably good efficiencies. And also, since they are exposed to structural stresses, high structural stresses because of the centrifugal forces, they require high-performance materials in production and maintenance. Recently, there is another family of the turbines which are oscillation-based turbines, and the main advantage of these turbines is that they even are able to extract energy in low Reynolds number currents with good efficiencies. Also, there is another advantage about using oscillation-based turbines. As you see here in this picture, the oscillation-based turbines in the right can extract the same amount of energy from the current compared to the horizontal axis rotation-based turbines in the right, even in less depths. So this is called shallow water advantage about the usage of oscillation-based turbines. The basic principle of the oscillation-based turbines leans upon flow-induced oscillations, which are of two general types, resonance type and instability type. In resonance type, the flow-induced forces and moments do not depend on the structural movement, which of this type, buffeting and vortex-induced vibration can be named. And on the other hand, in instability type, the flow-induced forces and moments depend on the structural movement, which of this type, flutter and galloping can be named. Here, I'm going to give you a short historical review about the prototypes made so far, oscillation-based prototypes. The first one was windmill, developed by McKinney and DeLaurier in 1981. This windmill worked based on flutter, aerodynamic flutter, and they tested it into the wind tunnel, and they concluded that this device can compete in efficiency with the conventional rotation-based turbines. The same scope of the windmill was used by Jones et al. In Naval Postgraduate School in California in 1999. They built this device and they called it flutter engine, which worked based on hydrodynamic flutter. They tested it into the water current flume. And also some industrial prototypes made based on hydrodynamic flutter. The most famous one is Pulse Stream 100, made by Pulse Tidal Ltd, and it is in operation since May 2009 in United Kingdom. Buffeting also was used by some researchers in order to extract energy from the water current. For example, this is energy harvesting eel, which is a piezoelectric energy harvester developed by Allen and Smith in 2001. And this is a yawing flat plate in the wake of bluff body, which is used to extract energy passively from the water current, developed by Fernandez and Armandi, 2011. And also, vortex-induced vibrations are used to extract energy from the water current. The most famous one is Vivace, developed by Bernitsas and Raghavan. And this device is a low-head hydrokinetic energy absorber. Galloping has two different types, translational galloping and torsional galloping. In the literature so far, there are some prototypes using translational galloping to extract energy of currents, but the main objective of this research is to introduce a new oscillation-based turbine which works based on torsional galloping. The potential of torsional galloping was proved first time during the collapse of the Tacoma Narrows Bridge in 1940, and it was known that the negative damping in the torsional degree of freedom was the main reason of collapse of this bridge deck. So we wanted to see if we can observe this phenomenon even in water current rather than wind. We conducted some experimental tests in the laboratory. Here you see the experimental setup. We used there is a rectangular flat plate attached to a torsion spring and with an axis in its mid-chord length, and we put this setup into the water current flume, and this is what we saw. I'm sorry. We saw that as we increase the water current, as the water current speed exceeds a critical velocity, the flat plate becomes unstable and starts oscillating torsionally about its axis. And here you see the transition from stability to instability. The blue line is the flat plate's time series, and the red line is the current speed. You see as the current speed increases from a critical limit, the flat plate becomes unstable and starts oscillating. So we wanted to use this idea to extract water current, energy from the water current. Our idea was to convert the oscillation to rotation and to use the rotary motion to do some physical work, just to prove the concept that energy extraction using this phenomenon is possible. So we designed a transmission box and installed it on top of the setup you just saw in the previous slides. Here is the mechanism of the turbine. You see this is the input shaft which gives the oscillation into the transmission box. This is the transmission box. This is the output shaft which gives the rotation out of the transmission box, and the rotation is used to lift this weight up to a prescribed height. Here I need to show one more movie just to see how the turbine works. You see here the output shaft which is turning, and the input shaft, the flat plate, which is oscillating torsionally. As the output shaft turns around, it rolls a string around itself, and the string is connected to the weight on the other side, and it makes the weight to be lifted up the height. Here you see the weight is being lifted, and this was how we tried to solve this in the mechanical engineering standpoint without using any electronic engineer, just to prove the concept. Sorry for the inconvenience. Equation of motion, here you see the equation of motion. I in this equation is mass moment of inertia, I66 is added moment of inertia, B is total damping coefficient, and K theta is torsion spring rate. In the right hand side of this equation, there is hydrodynamic moment, which is modeled here, considered here as a harmonic function, and this is the steady particular solution for the equation of motion, in which omega is response amplitude, response frequency, phi is phase lag, m0 and theta 0 are the amplitudes of hydrodynamic moment and yawing angle respectively. The total work done by the system can be calculated using the equation number 6, and the total power in each cycle of the oscillation is calculated using equation 7. If we replace m from m of the equation 7 from the right-hand side of the equation of motion into the integral, and also b with this expression, we come up with this formula for the total power out of the water current, in which zeta t is the total damping ratio. It has three different components: the damping ratio due to the structure, the one due to the transmission box, and also power takeoff damping ratio. So total power also has, if we replace it here, we find the three components for the total power. Also, we can set total power equal to the rate of energy, potential energy of the weight. Therefore, in this way, we can identify power takeoff damping ratio. Power takeoff damping ratio is indeed a dimensionless scale which connects the mass of the weight with the lifting rate here, and also, and in the end, with dividing the power takeoff from the current by the whole energy power flux through a projected area, which is CD chord length times the depth. Here we define the energy extraction efficiency. The experimental tests, we conducted them in for two different cases, each with different chord lengths and torsional spring rates. During the tests, we kept water depths equal to 0.45 meter, and also the axis, we kept it in the mid-chord length of the flat plate. At first, we conducted the decay tests once without the transmission system installed in order to find the structural damping ratio, and then with the transmission system installed in order to obtain the damping ratio due to the transmission box. Here are the damping ratios identified using the decay test results. Then we conducted the lifting weight tests in order to assess the energy extraction performance. During the tests, we changed the weight masses from 50 grams to 450 grams, and we kept the current speed equal a half meter per second, and also the lifting height equal to 2.2 meters. We captured time series of the flat plate for each lifting weight and also each case. Here you see two examples of the captured time series. You see, as you can see, it is so similar to harmonic functions. So we used the Fourier fast transform to find the response frequency and also equivalent harmonic angle to find the response amplitude. You see here the frequency ratio in the left-hand side compared and also the response amplitude in the right-hand side compared to the power takeoff damping ratio. As the power takeoff damping ratio increases, both frequency ratio and response amplitude are decreasing with the same rate, almost slightly for both cases A and B. And here you see power takeoff in terms of mass in the left-hand side and also efficiency, energy extraction efficiency in terms of power takeoff damping ratio in the right-hand side. There are two remarks about these two curves. First is that the case A with the a smaller chord length and also a smaller torsion spring rate is more efficient than case B. And the second is case B can lift heavier weight than case A. In conclusion, we introduced an innovative turbine which works based on torsional galloping. The advantages of one such device can be its simplicity in construction and also installation, and also its capability to work in low-head tidal and river currents. We tested two different cases and we concluded that the cases with larger natural frequencies lead to larger efficiency, whereas the larger mass and added moments of inertia, which is case B here, allow the turbine to lift heavier weights. And here are the things to pursue in the future. First one can be to see the effect of axis position of the flat plate in the performance. The second one can be to replace the flat plate with other profiles such as hydrofoils and rudder profiles. And the third one can be to use non-linear torsional springs rather than linear ones, which were used during this research so far. And in the end, I would like to acknowledge the national Brazilian National Research National Council because of funding this project. Thank you.